In the next part of section 2.3 on continuity, we're going to look at some other applications of continuity. Functions that are continuous. All constant functions are continuous. The following types are continuous at every point in their domain. So polynomials are definitely continuous. Rationals are continuous, provided the rational is not undefined at a particular value. Power function, root functions, trigonometric, exponential, and logarithmic. Functions f of x and g of x are continuous functions, or if they are continuous functions, so are the addition of them, the subtraction of them, the division of them, and the multiplication of them. The only thing you have to be careful is if we're dividing two continuous functions, the denominator cannot be 0. Okay, we're going to look at how we can make functions continuous. So we're given the following piecewise function, x squared when x is less than 1, 2ax minus 1 when x is greater than 1, and we want to find the value of a so that the functions are continuous. So we are looking for this missing constant in here. Okay, well notice that my domain changes at 1. Okay, so I need to concern myself with what's happening at 1. So I have to, for a function to be continuous, we know that the limit as x approaches 1 from the left of my function has to equal the limit as x approaches 1 from the positive side of the function. And furthermore, the value of the function has to equal this limit. So if we're taking a look at the limit as x approaches 1 from the left, I'm going to be using the function x squared because that is where x is less than 1. And we have to see or make this equal to the limit as x approaches 1 from the positive side. And that's going to be my function 2ax minus 1. So now substituting 1 in for x squared, I get 1, because 1 squared is 1. Plugging a 1 in for x here, I'm going to end up getting 2a minus 1. And now solving for a, I add 1 to the other side. And if I divide both sides by 2, I'm going to get a being 1. So if I put a constant in there of 1, 2 times 1, it'll be 2x minus 1. So the equation 2x minus 1 will make this function continuous. Okay, let's try another more challenging example, very similar. Now in this particular question, we are asked to find the variables c and d. So again, notice the first two functions, they change at the x value of -1, and the next two functions, they change at the x value of 3. So we're going to do the exact same thing we did in the previous example, except we have to do it twice. So we're going to have to say the limit as x approaches -1 from the left. And if I choose approach -1 from the left, I'm using the function x squared minus 3. And this must equal the limit as x approaches -1 from the right. And that would be the function cx minus d. Plugging in -1 for x, I get -1 squared minus 3 is going to be c times -1 minus d. And this ends up being 1 minus 3 is -2. It's going to be -c minus d. And if I multiply everything by -1, I'm going to get 2 is equal to c plus d. And that's as far as I can go with that one right now. But I can do the exact same thing with the value of 3. So I could say the limit as x approaches 3 from the left, again, I'm going to use the function cx minus d, has to equal the limit as x approaches 3 from the right. I'm going to use the function x squared plus 1. So plugging 3 in for x, I get 3c minus d. Plugging 3 in for x, I get 3 squared is 9 plus 1 is 10. So there is my second equation. So I have two equations with two unknowns. And if you recall from Math A30, we solved linear systems back in A30. So what I'm going to do is I'm going to rewrite my red equation as c plus d equals 2. And I'm going to write my blue equation underneath, which is 3c minus d is equal to 10. And if you notice, I've lined up my c's, my d's, my equal signs, and my constants. And now I'm just going to add. So 1c plus 3c is 4c. These are going to cancel, and this is going to equal 12. And if I divide both sides by 4, c is going to be 3. Now, once I have my c value, I can go back and find d by choosing any one of the two equations. I'm putting a 3 in for c, and solving for d, I get d being -1. So again, this question a little bit more challenging, but really the same process. We just have to do it twice and then solve a linear system. Okay, let's take a look at the next example. We have the function f of x, which equals 6x squared plus 18x plus 2, or 12, sorry, divided by x squared minus 4, and it's not defined at plus or minus 2. What value should be assigned to f of -2 to make the function continuous at this point? Okay, well, first things first, let's factor out a 6 out of my numerator, and I'm going to get x squared plus 3x plus 2. Bottom obviously factors into x minus 2, x plus 2. And we can go one step further. This factors into x plus 1, x plus 2. And again, this is going to be x minus 2 and x plus 2. Now, we know that the function x plus 2 and x plus 2 are going to cancel out, but I still have my restrictions of plus or minus 2, which is stated in the question. So right now I have a hole in the graph at x plus 2, or at the x value where x is -2. So if I want to figure out what to assign to f of -2 to fill that hole, I have to now evaluate the limit as x approaches -2 of what's left, which is 6x plus 1 over x minus 2. And I can use direct substitution. It's going to be 6 times -2 plus 1 all over -2 minus 2. So this ends up being -1 times 6 is -6 over -4, which is going to be positive 3 over 2. So therefore, f of -2 should equal 3 over 2, so that the function is now continuous at the point -2. Okay, let's f be the function given by this piecewise function. If f is continuous at x equals 5, then what is the value of c? Okay, again, if we look at this function, it behaves like the top function if x doesn't equal 5, and it behaves like the constant if x is 5. So this down here is simply a point. And remember our definition of continuity. There has to be a value of the function at 5, and the value of the function at 5 has to equal the limit of the function at 5. So the first thing I'm going to do is I'm going to calculate the limit as x approaches 5 of the square root of x plus 4 subtract 3 over x minus 5. And again, if I was to use direct substitution, I would get 0 over 0. And if you recall from our earlier section on limits, this one here, I have to multiply by the conjugate of the numerator. So this is going to equal, and remember we only multiply out the conjugates. So root x plus 4 times root x plus 4 is x plus 4. When I multiply the conjugates, the middle terms will cancel, and minus 3 times positive 3 is minus 9. And this is all over x minus 5 times the square root of x plus 4 plus 3. So now if I was to collect like terms up top, I would end up getting a x minus 5. So this x minus 5 is going to eliminate that, x minus 5. And I'll be left with a 1 on top. And now I can directly substitute in 5. So I'm going to get 1 over the square root of 5 plus 4 plus 3. If I evaluate that, that's going to be 1/6. So therefore, c would have to be 1/6 for this function to be continuous. So the hole created by the discontinuity is filled in by this point right here. Okay, this is an actual AP multiple choice question. And in this question, it says, let f be a function defined above. For what value of b is f continuous at x equals 2? So this is the exact same question that I had earlier. So again, this is a point. And if I wanted this to be continuous, the limit up here has to equal the point down here. So I'm going to calculate the limit as x approaches 2 of x squared minus 7x plus 10 all over b times x minus 2. So again, I could factor the top, and the top will factor into x minus 5, x minus 2 over b times x minus 2. So again, at 2, I do get a restriction, and 2 would be a whole because the factor of x minus 2 cancels out. So now I need to calculate the limit as x approaches 2 of x minus 5 all over b. And if I plug a 2 in, I get negative 3 over b, okay? And I cannot solve this equation. So there really is no such value of b that's going to make this true. So therefore, this is the correct answer. Okay, let's take a look at how we find and classify points of discontinuity. So in this example, or these examples, we're going to have to figure out where the discontinuities are, and then we're going to have to classify them and verify why they are the discontinuities that we say they are. So first of all, I have a restriction, and that's going to be our first starting point here. X cannot be negative 1. If I was to plug negative 1 into my function, I'd get 0 over 0, so it's indeterminate. So the next thing I'm going to do is I am going to factor, I can factor the top as a sum of cubes. And now, because the factor that has the non-permissible value of negative 1 cancels out, this is going to be a hole in the graph. And so since it's a hole in the graph, it's going to be a removable discontinuity. And to exactly show where that hole in the graph is, we can calculate the limit of what's left as x approaches negative 1. And this is going to work out to be 3. So I have a removable discontinuity at x equals negative 1, and the hole in the graph would be at negative 1 and 3. Okay, in the next example, same idea, but before we list the non-permissible values, it might be advantageous to factor this. So again, I have x plus 4 in the numerator, all over x, and I have a difference of squares still. So I have 3 non-permissible values. X cannot be 0, 2, or negative 2. And note this factor of x, which is related to my factor of our non-permissible value of 0, cancels out. So that's an indication that I am going to have a removable discontinuity at 0. Now to figure out where exactly that removable is, I'm going to find the limit as x approaches 0 of what's left. If I put 0 in for x, I'm going to get 4 over negative 4, which is negative 1. So the hole in my graph is going to be at 0 and negative 1. Now, if I analyze what's left, the x minus 2 and the x plus 2 do not cancel out. So those are going to still be non-permissible values, and they're going to show up as vertical asymptotes. So I have infinite discontinuities at x equals 2 and x equals negative 2. And to verify, you could plug a 2 into what's left, and you would get 6 over 0, which indicates that's a vertical asymptote. And if I put negative 2 in, I'd get 2 over 0, which would also be indicating it's a vertical asymptote because I end up with a number over 0. Okay, in this next example, we're looking at a piecewise function. And when we're looking at a piecewise function in regards to discontinuities, look at the individual function itself. X squared is continuous on its own. It's a parabola. 2x plus 1 is continuous on its own because it's a line. So the only place that this thing might not be continuous is going to be at the point where it changes, and that's at 2. So we're going to go through the definition of continuity for 2. So number 1, I have to figure out if there's a value of the function at 2. And to do that, I would use the top function because that's where it equals 2. and that limit is 4. Secondly, I'm going to figure out if there's a limit as x approaches 2. And to do that, I would have to figure out the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. From the left, I'm using x squared. If I plug a 2 into x squared, it's 4. If I plug a 2 from the right, I'm using the function 2x plus 1. 2 times 2 plus 1 is 5. So therefore, the limit at x equals 2 doesn't exist. And since the limit from the left goes to a different limit than the right, that concludes that we have a jump discontinuity at x equals 2. All right, the next example, I'm going to encourage you to pause the video and try this one on your own because this one's very similar, so I'll give this one a try. Okay, I'm hoping you had a chance to try this one. And again, notice that these functions on their own are all continuous, so the only places that they might not be continuous are going to be at their change points, so 0 or 1. So just like the previous example, I'm going to go through the three-part definition of continuity for these 3 points, or these 2 points, sorry. So first of all, part 1, is there a value of the function at 0? I'd use the top function, and the value of the function is 4. So is there a limit as x approaches 0? Well, again, I'd have to do the limit from the left, and I'd have to do the limit from the right. Coming from the left, I'm using x squared plus 4, and we found that to be 0. Coming from the right of 0, I'm using the function x plus 1, and if I plug a 0 in, I get 1. So since the limit does not exist, it is not continuous at 0. In fact, I have a jump at x equals 0. So there's my first discontinuity. So now I'm just going to go to a new page, and I'm going to do the exact same thing for when x is 1. So statement number 1, I have to check, is there a value of the function at 1? And to figure out the value of the function, I'm going to use the top equation. So this is going to be x plus 1, and if I plug a 1 in, I'm going to get 2. And again, I have to figure out if there's a limit as x approaches 1, and because it breaks at 1, I have to check the limit from the left and the limit from the right. So less than 1, I'm using x plus 1. Bigger than 1, I'm using x squared plus 1. If I plug a 1 in there, I get 2. If I plug a 1 in here, I also get 2. So therefore, my limit as x approaches my function is at 2. And since f of 1 equals the limit as x approaches 1 of the function equals 2, therefore it is continuous at x equals 1. So therefore, I really only have one discontinuity, and that only discontinuity is at 0, and it's a jump discontinuity. Okay, one of the last examples is we're dealing with an absolute value. And again, remember, we need to go through the 3-step definition. Again, let's take a look at where our non-permissible values are. Well, first of all, we know that x cannot be 5. And we know if I was to factor inside the absolute value that I would get x minus 5 and x plus 4 all over x minus 5. So that would be my function. So if I was to plug a 5 in, I would get 0 over 0, which is indeterminate. Okay, so let's go and see if I can find a limit here. So I want to find the limit as x approaches 5. Now what we need to be careful of here is I have an absolute value. So the first thing I have to do is I have to remove the absolute value because I need to figure out the limit coming from the left, and I need to figure out the limit coming from the right of 5 to see if they're the same. So if I was to take out what's inside my absolute value, the x minus 5 and the x plus 4, and create a number line. Again, if I was to put in negative 5, they would both be negative, would be positive. If I was to put in 0, it would be negative and positive, and 6 would be positive, positive. So when I'm finding the limit as x approaches 5 from the right, I'm going to use the positive branch of my absolute value. So this is going to be x minus 5 times x plus 4 over x minus 5. So these are going to cancel. 5 plus 4 means my limit coming from the right, is going to be 9. Now, if I approach 5 and the limit's coming from the left, I have to use the negative of the absolute value. So the x minus 5's cancel. So this is going to be the negative of x plus 1. That should be a 4 there, sorry. So this ends up being negative 9. So the limit from the right of 5 is 9. The limit from the left of 5 is negative 9. So therefore, I have a jump discontinuity at x equals 5. Very often when we have an absolute value function within our equation, we are going to have a jump discontinuity. Okay, in our last example, this is from the 2019 AP Calculus exam, and we're just going to look right now at question D, okay? And question D is saying functions f, g, and h are twice differentiable, and g of 2 equals h of 2 equals 4, so that's important, okay? And it says we're given a line, and that the line is tangent to both the graph of g at x equals 2 and h at x equals 2. Okay, so in question D, it's known that g of x is less than h of x for 1 to 3, and k, let k be a function satisfying satisfying the inequality that g of x is less than or equal to k of x is less than or equal to h of x for 1 to 3. The question is asking, is k continuous at x equals 2? Okay, so we're trying to determine if k is k continuous at x equals 2. So I need to go through the three-part definition. Okay, so I have to first of all figure out, is k defined at 2? And is there a limit as x approaches 2 for the function k? And if are those two things equal? Okay, well, there's a couple things we can look at here. Okay, first of all, if g of x is less than or equal to k of x is less than or equal to h of x, okay, we know that g of 2 is equal to 4 and h of 2 is equal to 4. So we know that g of 2 is equal to 4 and h of 2 is equal to 4. And if k of x is between these two, it makes sense that k of 2 also has to equal 4. So I've shown that the value of the function at 2 is 4. So now I have to show that the limit as x approaches 2 of k of x is also equal to 4. Okay, to show that the limit as x approaches 2 of k of x also equals 4, we have to go back to the original question and look at this statement. It tells us that f, g, and h are twice differentiable. So if f, g, and h are twice differentiable, that means they are continuous. So if g or f of x and h of x are continuous, and g of 2 and h of 2 is 4, we can conclude that part 2, the limit as x approaches 2 of g of x is going to be less than or equal to the limit as x approaches 2 of k of x has to be less than or equal to the limit as x approaches 2 of h of x. And so we're going to use an application of the squeeze theorem. And again, since g of x and h of s are differentiable, they're continuous, so their limit has to equal the value of the function. So we know that this is 4. and we know that the limit as x approaches 2 of h of x is 4. So by the squeeze theorem, it concludes that the limit as x approaches 2 of k of x is also 4. So I've met part 2 of my continuity definition. And by part 3, since k of 2 equals the limit as x approaches 2 of k of x, and they both equal 4, therefore k of x is continuous at x equals 4. So again, that's a little bit of a more challenging question, but again, just to show you where it can be used on the AP exam moving forward when we get to the exam in May. Okay, so there is the assignment on continuity from section 2.3. So we have both textbooks. The top textbook is your AP textbook. The bottom assignment is from your Calc 30 textbook. Again, if you have any questions, feel free to check the website for your answers.